Oh, the shades. The other way, going this way. Okay, let's continue with probability, the second section. Last time we spoke about independent events and mutually exclusive. Do you remember what those are? A and B. These are events are independent if, how do you know it's independent?
One does not affect the other.
When the outcome of one does not affect the outcome of the other, what's an equation that describes the situation? P of
A times N B.
and B is
P of A times
product, right? So remember that does not work in general. That's just for independent events. We have also mutually exclusive. Means what's the mutually exclusive? P of A and B is what?
P
What
of
does mutually exclusive mean? Exclusive.
the outcome of one does not
One excludes the other. So what's the probability of both of them happening? Zero, because if one happens, the other won't, right? That's called mutually exclusive. So those were some things we looked at. We also looked at the law of disjunction. That's another point to remember. For two events, disjunction. That's the one that told you what P of A or B means. What's that?
P of A
Plus P of B. Minus
P of A B
P of A and B. You have to know these formulas, very important. You're not going to be given them, you have to remember them. And if we're mutually exclusive, then P of A or B is what? You just add them. Right? Because the intersection part will be zero. Right? So it's very important that you, one, know when to recognize one of these situations are happening, and two, to know what equations go with those situations. You'll have different ones. So this is the general formula for probability of A or B. However, in the special case where you have a mutually exclusive event, you just worry about adding them. Or becomes add. Right? In the case of independent events, and becomes multiply. Right? You can directly translate this. So if you want to know probability of something and something happening, you just multiply them. Once you know these things, one thing doesn't affect the other. Right? Something or something, if you know two things cannot happen at the same time, you just add the probabilities. Multi-staged experiments are both. Right? That's why back in probability section 1, we could have done, think of and as this and or as adding, because a multi-stage experiment tends to be both if you're only talking about one object. Okay, so those are just some of the things we did, and we did examples where we used all of these. So now we're going to move on to conditional probability. It's also a very important concept, has its own formula. Let me just give you the equation and then I'll talk about it. We denote the probability that an event B will occur that doesn't given that B has already occurred, by B of A. There's a straight bar and then a B. This is red. Probability of A given B. Right? So that's the notation. The probability of A given B. Basically what this means is what is the probability that A will happen given that B has already happened. Right? So sometimes things work out in terms of conditions, right? Meaning the chances of something happening might depend on something that happened before, right? So whenever you have this sort of situation coming up, then we say we have a conditional probability. That's what it is. This is given by the following formula. Probability of A given B is equal to the probability of A and B over the probability of B. That is the formula. And of course, I can extend this. So that's equal to the probability that A will occur. Already occurred. Now, we sort of did this before, but I never really explained it in this way. Remember when we were doing those, that question about people having a couple of kids, they have two girls, but there are tons of ways they can have a girl.
Yeah.
Right? The difference why those probabilities why all those values are different is because we were given different conditions. There were different conditional probabilities. It wasn't the same guy. You always had something else, even though the subject matter was the same. So I was like, what's the probability that I have two girls? That's something different. And then I said, what's the probability that one of the, if you know one is a girl, the other one is a girl, right? What I did was I put in a condition, right? How do we know if they have a girl, given that situation, what's the probability that they have another one, right? And then I was like, what's the probability if you know that the older child is a girl, the probability that the other one is a girl? That's a different condition, right? Now you're taking the condition that a girl happened first. It was different from just a girl happened at some point, and the condition that a girl happened first are two different conditions. And that's why the answers were different, right? What I was really doing was conditional probabilities. We did it through a diagram, so we never had to use this formula. We could tell from the diagram. But there are cases where, like I said, diagrams are inefficient, and so we'd like to have a formula for things. And so for conditions, if you know you're figuring out if something happens based on a condition that something else happened, this is the formula you use. And the formula actually reduces if A and B are independent. Then the probability of A given B is just equal to the probability of A. Independent means one doesn't affect the other. So given that B already happened, what's the probability that A will happen? Well, just the probability that A will happen. B happening doesn't affect us at all, right? And you can think of the Y, well, that's because the probability of A given B is equal to the probability of A and B over the probability of B. But this equals if they're independent. Then the top you can write as probability of A times the probability of B over the probability of B. B's will cross out and you just get A. Right? So in the case that B doesn't affect A at all, then this happening doesn't affect anything. It's just the original probability of A. So that's a shortcut that you can use. And it will also help you answer various kinds of problems, just knowing that. So for example, let's do an example where we use conditional probabilities. So there's both an intuitive reason why this is true and a mathematical one. It's consistent. So let's talk about an example. I actually stole this problem from the book. It's 13 from the text. It's a nice problem. I'm not sure if I actually assigned that for homework or not. Okay. So, college freshmen are required to take courses X and Y, right? Math and English or whatever. And we know from statistics that 15% get an A in course X, 10% get an A in course Y. And we know that 23.5% get A in one or the other. And here are the questions. Right? So we have two courses. Every college freshman have to take these two courses. We know that 15% of students who take course X will get A's. Only 10% who take course Y will get A's. Overall, if you count the this has 2 semesters, an average of 23.5 students will get A's in either one or the other, right? Not necessarily both, one or the other. And now here are the questions. What fraction of students get A's in both? Okay, that's the first question. So you know. If you want to know what's the odds that if you take these two courses you'll get an A in both of them, sort of gauge how much study time you want to commit to this course. What is the probability that a student who gets A in course X will also get an A in course Y? C is receiving an A in course X independent. And of course, justify your answer. Don't just say yes or no, but explain why. Give you a little time to copy that down, and then we can begin. So we're required to take 2 courses. You know all the stats of getting an A. Need to know how many of us will get A's in both. Well, it's probably that if we get an A in course X, we'll also get it in course Y, and is this an independent event? So this is where we're saying, what are the chances I get A in both courses? And then you're like, okay, what if I do well in this course? Will I also do well in the next course? And then you're going to ask the question, is this independent? Right? Meaning, does my grade in Y actually depend on my grade in X? Is it true that if I do really well in this one, I will have a good chance of doing well in that one, right? That's sort of the question you're asking here. And in the case that they're not independent, then you probably wouldn't really care. But if you really want to get A's in both, and you know that getting an A in this depends on that, then you'd study really hard for this to better your chances for that. So it's about strategy. You know, so, these are actually pretty logical questions to ask if you're really trying to be strategic about your GPA and things like that. Okay, so what fraction students get A's in both? First, let's name these events. How do we want to call the events? Well, the course name is X. I don't really want to call it X.
A.
How about AX? Equals event and A is received in X. Call it AY event and A is received in Y. Okay. So we are told some pieces of information, right? The probability of getting an A in course X, the probability of getting an A in course Y, and we're told the probability of getting an A in course X or course Y. What's the information we're told here? 15%, which is 0.15, or they asked us for a fraction, so you could probably write this as a fraction, 15 over 100. AY was 10%, that's 0.10, which is 10 over 100, or 1 over 10, but I can leave it in the same denominator, just in case you want to transfer. So this is 0.235. Okay, so now let's answer part A. Right, so we read the question carefully, and then we copy down all the information we know. This is actually a good strategy. So just put it out there, everything you know, because you never know what you might need. You start to pick the numbers. It's much easier to pick up your information from this than to be rereading the question all over. What did it say again? All right, so you just copy this down. Okay, so what do we want to find first? What is part A asking us for?
I'm getting A in both classes.
Right, so that would be the probability of what?
AX
A
plus AY.
AX and AY, right? That is what part A is asking us for, right? It's a, what is that, right? So recognize what you have and what you need to find, right? That's half the battle. Okay, so I know what I want to find. I know what I'm given. How do I make it work?
Because they're independent? Or
How do you know they're independent?
Because they're different? Because we don't know for certain.
We don't know. Which means you cannot assume you have to multiply.
So just to multiply, then subtract the.
So P of AX plus P of AY minus P of AX times P, or times AX?
You can't do times. You don't know if it's independent or not. In fact, part C is asking you about independence, which means in part A we don't even know.
I was trying to.
Give me a formula to use.
Yeah,
The disjunction formula.
that's what
I know
was trying to say.
That P of AX or AY is equal to P of AX plus P of AY minus P of AX and AY. Right? So I know this, I know this, I know this. They're asking me for this. Just solve the equation. So P of A or is this 0.235. P of A I know is 0.15. P of AY is 0.1 minus P of AX and AY, which means that P of AX and AY is equal to 0.15 plus 0.1 minus 0.235. And what's that?
What?
I just bring this over here, brought this over there.
Oh,
I'm solving the equation for the and. So what do we get? That's 0.25 minus 0.235.
0.015.
They asked for it as a fraction. How would you write that as a fraction? Well, it's 15 out of 1,000. And you can reduce it if you want. 5 into 1,000 goes 3. 5 into 15 goes 3 times 5 into 1,000 goes 200. So 3 over 200 is the fractions, right? So you know 3 out of every 200 students will get an A in both courses. So the odds aren't that good for getting an A in both courses. These courses must be really hard.
where to start?
So you're like, yep. Now you got to prepare. You're like, the chances of me doing this right are slim. I better prepare. But what's the best way to prepare? Study really hard for X, because that would sort of give me a good chance in Y. We don't know yet. So let's actually do this. Which one should I focus more attention on?
X.
How do you know? We don't know yet. That's what we're going to figure out in B.
I thought you meant first study. But continue.
Yeah, well, we don't know yet. We will only know that answer really when we get to part C.
Are they the same?
What is part B asking for?
Are they both like math courses or bio courses? Calculus courses, or are they completely separate subjects?
What is part A asking for?
B.
What are the chances of getting an A in X if you already got one Y?
Write it down in probability notation. What would it look like?
Probability of A. Probability of A given B, right? Or S. Probability of
AY.
X given AY.
AY given AX, right? Remember that in the notation, the part in the last part comes first, right? Happens first. Right, so we're like, what is the probability that if you get an A in X, which happens first, then you will get an A in Y, right? So what's probably you'll get an A in course Y given you got an A in course X, right? And how would we do that one? Let's do the formula. So what is this? P of AY and AX over P of AX. So what are those numbers? 0.015. That's what we actually found in part A.
Yeah.
Divided by the probability of getting an A in course X.
0.15.
This is 0.15. So what's that, 0.1?
Yeah.
Yeah. 10%.
That's a good.
For AX.
Yeah. So if you get an A in course X, there's a 10% chance you'll get an A in course Y. But is it all worth it? What do we have to do this? We're going to use this in my life.
If that's the case, you change the major.
So is it actually independent? Ah, but we would know by now. Based on our answers to A and B, we should know by now. How would we know by now?
I would
No,
say
they're not independent because they're such small.
Yeah.
The size of the numbers doesn't matter.
So what matters? Well, one might come over the
If they're mutually exclusive.
If AX, and we didn't ask about mutually exclusive, we asked about independent. By the way, we know they're not mutually exclusive. How do we know?
Because the law of disjunction is that with that value.
Because probably if and is not 0. So they're definitely not mutually exclusive. Are they independent though? If these were independent,
one would affect.
then what would be true? What would the conditional be, for example? What would that have to be?
P O.
Oh, P of A.
A what?
A Y.
AY.
Just P of AY, right? If these are independent, then what you got in course X just wouldn't matter, right? It was just the probability of getting A in course Y. So this is equal to, we were given 0.1.
Oh, that's the same,
It's the
yeah.
same thing.
Oh, but that's actually equal to the probability of AY given AY and AX. Well, we are, which is true.
Is there a chance for coincidence?
So they are independent.
Could it be a coincidence?
Not as far as the math is concerned.
But
That's no.
So basically this says
why?
how well you do in X doesn't matter for Y. Right? So it's not like doing better in X will cause you to do better in Y. So basically the conclusion is we're screwed. There's a very small percentage that will get A in both, and studying hard for one doesn't help us for the other one, so tough. Switch majors is another option. D, should we switch majors? Okay.
Go get a job.
Just get a job. Just drop out and get a job. I don't really want to do anything with this, but I should probably just tell you anyway.
Jhevon?
Yes.
That was my question. So, could you also do that they're independent if you said the probability of A plus B equals probability of A times probability of B?
Yeah,
And we would get the same answer?
you should, yes.
Yeah.
You would get the same answer. I could do that. Or if you want to use the straight up definition, check if probability of A, Y, X and A, Y is actually equal to the probability of AX times AY. That is another option, perfectly valid. This one we know is 0.015. This we know was, I erased it, I think that was 0.15
And 0.1.
and 0.1. And when you multiply these, you do in fact get 0.015. So again, it will check out that they're independent. Yeah, one does not affect the other as far as we can tell. We actually rarely get tested on this, and it's sort of just one of those things, you know, if you have all the pieces for it, you use the formula. But I'm just going to mention it and move on. It's a very important formula, but it's not in our syllabus really. Bayes theorem. Basically, it gives us this huge formula in terms of conditionals. It's going to be P of A given B. Another way to find that is P of B given A times P of A. So this is sort of the angle you'd come from if you don't really know the AND probability, but you actually know how the things operate in reverse. You know what the chances of getting B happening given that A has happened, but you don't know what's the probability of both happening at the same time. You can sort of attack the problem of A given B by this formula. We hardly ever use it though. So it's important to know, like, you know. And that actually ends chapter 11, which means the next test is next Monday. Today's what? Today's Wednesday. Next Wednesday. The review problems are already up. So, test next Wednesday, April, is it? Are we still in April?
Yeah.
April 29th. No, will we still be in April next Wednesday? So that will be the third test, and anyone has the syllabus? It'll cover, I think, from regression. No, it covers everything from 7 to 11. So everything from like histograms, when we just, well, basically everything we've done from statistics to now. Being able to do the bins problem and estimate mean, median, mode is really important. Being able to draw a histogram or a box plot. Being able to find the regression line, being able to compute standard deviation and all of that stuff, mean, mode, mean, and all the probability stuff. That will be on the test. You know, questions like, you know, choosing a balls from a box or something like that, those are popular, so know how to do those. The rolling of the dice, the flipping of coins, things like that. Yeah, so that will be Wednesday. So, what? So we're going to skip chapter 12, which talks about genetics. It's not like most of you are in bio anyway. And we're going to jump right to chapter 13, where we shall be introduced to the concept of a random variable. More specifically, a discrete random variable. Random variables 1, which is discrete random variables. We use a definition here. It's not a general definition, it's more of a simplified one for our purposes. So we're going to be very specific. A discrete random variable. One that can take on in such a way that if an experiment is done, only one of these values So we sort of spoke about it in terms of probability. But discrete in general sort of means you can only take on certain values in a range, right? So if you have like the range from, like if you take the interval of 0 to 5, for example, and then you ask, what is a discrete variable on this interval? Well, the integers is an example of a discrete variable, right? Because integers can only pick certain values from that range. 0, 1, 2, 3, 4, etc., right? A real number would not be a discrete variable, because a real number can take on any value in that interval it chooses, right? Anyone's fair game. The integers can only pick certain values, right? If you pick 2.5, an integer can't pick that value, right? So integers are an example of a discrete random variable, right? They can only pick on certain values in a given interval. A real number would be an example of a continuous random variable, which we'll do later on, and it can take on any value in a certain range. So basically a discrete random variable, how we'll use it, it takes on certain values, but we're looking in the context of probability. We're doing an experiment. If you do it once, there's only one possible value out of a certain list of values that can happen, and only one will happen for each experiment. We call a variable that measures that, a discrete random variable. So there are many of them. Example. In the case of dice, we have a discrete random variable, right? You roll a dice, a fair six-sided die, there are only 6 possible values it can take on. Can't take on any number at once. There's a specific list of 6 values it can take on. And every time you roll a dice, it can only take on 1 value for that roll, right? So then that means it's a discrete random variable. So if I can say let x be the number of the upward face of a roll, die, then x is a discrete random variable. It may only take on values from the set of 1, 2, 3, 4, 5, 6, and only one of these values for each row. So the numbers on the face of a die, and if you let x be a variable that can measure the numbers, it has to be a discrete random variable. It can't pick any number in some interval it wants. It has to pick one of these 6 numbers, and it can only pick one at a time. Right? A variable that does that is called a discrete random variable. It's important for us to identify these because there are certain formulas that will only work on these variables, and there are other formulas that will work on other kinds of variables. So we should know when one of these will happen. So let's continue running with this example. 2 dice are tossed. Let x equals the sum of the upward numbers. We're assuming it's a fair dice, right? So all possibilities. What are the possible values? For x. We've actually done something like this before. I actually did that table, right, where we went 6 across this way, 6 down, and we added all the numbers in the middle, right? So we have seen that x may take on values in a set of 2, 3, 4, 5, all the way up to 12, right? This is if we get 2 1s all the way up to the possibility that we get 2 6s. And we saw something else. The probabilities. We saw that the probability that x equals a 2 is actually equal to the probability that x was a 12, right? Which was, what was that, 1 out of 36? We saw that the probability of x equals 3 was equal to the probability that x equals 11, right? With what probability? 2 out of 36. Probability that your sum is a 4 was the same as the probability that the sum was a 10. It's 3 out of 36. Probability that your sum is a 5 is equal to the probability that the sum was a 9, which is 4 out of 36. Right, and that's 6 and 8. Probability that x equals 6. Probability that x equals 8. This was 5 out of 36. And then finally we have the probability that x was a 7 stood alone, which was the probability that we had 6 out of 36 possibilities. So in this situation, I have this discrete random variable x. I know it can take on these values. We did the table before, and we found the probabilities in an earlier example when we started chapter 10. Right. And we found that these are the probabilities. Some of them were equal. And given this information, there are a couple of things we can do. Just like how in statistics, when we had all this data, we want to represent it in a convenient way to be able to answer questions. We're going to do the same thing with probabilities now. If you're given just a bunch of probabilities, looking at this sort of gets confusing. So what you can do is you can, for one, put it in a table. The table is called a probability distribution. And we'd be able to draw a diagram from it too, a graph, a bar chart, all that stuff that we did with statistics, we can do again with probabilities. So I'm just going to start to introduce that stuff. The probability distribution. We can put these values in a table. Showing the values of x and the probability for each. So, and that's called a probability distribution. So it would look like this. You'd have x and the probability of having that x. So in this case, our values were 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we put in the probabilities for each. So the chances of this happening were 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, and then it started going down, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. So we had a peak at 7. So when we put our probabilities in a table like this, where we list all possible values of x, and then we list all the probabilities for each one, we call that a probability distribution, right? Sort of the same idea behind a frequency table, except now we're looking at the probabilities of something happening, not necessarily the frequency of it happening, which in some cases is sort of similar, right? The frequency would be the upper portion. Okay. And then the probability is sort of like the relative frequency. It's essentially equivalent. Right? So they play well together. So again, one might argue that this table still might not be too efficient. Right? It's still a long table. So looking at this is annoying. Looking at that can be also annoying. So then we come in with pictures. Right? And we can do what's called specifically a probability histogram. So basically a histogram, except we plot probabilities, not relative frequency. Okay, so good chart always have a title, histogram. For the sum two dice. So basically this, on this side we're going to have the probability. And on this side we're going to have the values of x, which x would have been named before. Sum of two dice x. So it can be a 2, or a 3, or a 4, or a 5, or a 6, or 7, or 8, or 9, 10. We can have 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. So 2 can happen with 1. It's sort of like it's more like a bar chart. We put spaces between the bars. 3 can go up to 2. 4 can go up to 3. 5 can go up to 4. 6 can go up to 5. 7 can go up to 6. 8 can go up to 5. 9 can go up to 5. If you want, you can shade these, but you don't have to. Just for contrast sake. So remember, a lot of times probably we're dealing with a lot of data, just like in statistics. So we want to get away from being able to write probabilities at like a list like this. Sometimes we want to be able to write it in a table called a probability distribution. Know the name because they'll ask you for it in questions. They'll say, what is the probability distribution? It means they expect you to draw a table, right? Or you can draw it in a diagram, just like a histogram, except here you're plotting probabilities versus the values instead of relative frequency, which essentially is the same thing. But this is called a probability histogram. And from here we can just look at it and tell, oh, the chance of getting a 7 is higher than anything else. We can just tell that at a glance. Instead of to look through the table and discover that, you'd have to actually read all the numbers and be like, okay, that's the biggest one. Right here you can just see it right away. So depending on how efficient you want to be, and sometimes you can even put the values on this. So you can put this as 6 out of 36, 5 out of 36, etc. So when someone sees where the biggest one is, they can just see the number right here. Oh, those are the chances of getting that. So optional, more or less. But it's a nice thing to do. It helps your reader a little bit. So they can get both the information from a table and the graph all in one shot very quickly. 5 out of 36. 5 out of 36. 36. These are options. Just make sure if you're drawing the graph, you line things up correctly, so I know you have the right answer. So those are two things we can do. So we've been through that example before. Here's another example that is similar to something we've done before. Let's sort of try to rephrase it in this language. because this language is going to be more efficient for us later. Their coin is lost 4 times. Let x be the number of heads obtained. Find the probability distribution for x and draw the probability distribution. That's something I should mention. How do we know that x is a discrete random variable? Well, the number of heads can only be certain values. None, 1, 2, 3, or 3. Right? Can only pick from those values. And in every 3 tosses, it can only take on one of those values. So it's a discrete random variable. Which means, let's call this A, call this B. You can probably fit A here. When you guys copy that down, we'll continue. Okay, let's do the probability distribution x versus p of x. What were the possible values of x?
That's it, sorry.
0, 1, 2, 3.
X is defined as the number of so possible values of x have to be numbers.
3.
0, 1, 2, 3. Just list all the possible values you can take on. Right? They will be numerical values usually. And what's the probability of getting no heads? Remember what the total number of possibilities were?
Out of
It was 8, right?
8.
You're tossing 3 times. There are
Yeah,
3
two.
stages. Each stage has 2 options, so it's 2 to the 3. So there are 8, and there's only one way to get none. So that's 1 out of 8. That's in the case that you toss all tails. That's the only way to get no heads, right? What's the probability of getting 3 heads? Also 1 out of 8. There's only one way to get 3 heads. You have to toss 3 heads. Okay, how many ways could we have gotten 1 head?
Top, middle, left.
Right, could be either on the first toss, or on the second toss, or on the third toss. There are 3. How many ways can we get 2 heads?
3. Because there's 8, so 3 with 1.
Right, you could actually figure that out. That's something I wanted to mention. So this you automatically know is 0 out of 8. Don't waste your time counting again because it's a probability distribution. So we know what all the probabilities should add up to.
1.
They should all add up to 1. So if I have this, this, and that, what is this? Just subtract all of these from 1. Don't waste the glycogen in your brain trying to figure out, oh, well, I can get the first and second, or the second and third.
Yeah, which one of your students sounds like
The proverbial student in my head sounds like, Jhevon, you have to study, do you have to notes for the test? What do you need this mother? Okay, notes. Let me just mention that specifically. The sum of the probabilities must be 1. There is no choice. Must be 1. by we mentioned this before, the 0-1 principle. This often helps you in your calculations. So if there's one situation that's missing that it's sort of hard to think about, well, if you know all the other situations, you can figure it out because you know they must all add up to 1. Right? So you just take 1 and subtract all the probabilities that you know, and the result should be the probability that you have left to figure out. Right? So that's a very useful thing to know. So know that they must be 1. So that was part A. Part B is to draw the histogram. Histogram showing number of heads. Or I could say it's not really a number of heads, the chance of heads. Probability histogram for the number of heads, which we call x. So we can label that by x. Possible values are 0, 1, 2, 3. And the chances of 0 is 1 out of 8. Chances of this is 3 out of 8. So that's it. So 0 is 1 out of 8. This is 3 out of 8. 2 is 3 out of 8. 3 is 1 out of 8. There's also the idea, and we'll come back to this, not necessarily here, where the areas of all the pieces should add up to 1. Right? If you can actually scale things so that that happens, and then you can use area to help you with figuring out probabilities, which is a concept we will do, but we mostly do that for continuous random variables. That's going to be a big thing when we get to normal distributions. We're going to actually figure out probabilities using area. But for this case, that's it. So probability distribution, just the table, list all the possible values, list the probability of each value. You throw these on a histogram, which should be fully labeled, and you get what's called a probability distribution. Probability histogram. Okay. Let's just ask you some more questions on a probability distribution. See a random table, how do you know it's a probability distribution? That's only 2 examples. Let me make up a third. Just to mess with your heads. See. Did everyone get the histogram? Scratch right here, 0.01, 0.6. What? You have a question? Okay, we are starting here. So answer yes or no and justify your answer. Are the following probability distributions?
No.
No. Why is it no?
X total is 1.05.
If you sum the probabilities of x, you get 1.05,
0.05.
which is not 1. You cannot have all the total
Maybe it's
possibilities.
2.5 here.
There's a 105% chance this will happen.
1.25.
1.25? 110% sure. That's good in language, not in math. Okay, so what about this one?
Yes.
Yes. The sum of the probabilities was 1, right? What about this one? Why not?
How can you get probability?
No. So the sum of the probabilities here was 1, but we have the probability of 3 is equal to minus 1/4, which is crazy. So we can't have a negative probability. Any questions on that?
1.6. Yes.
So now we're given a variable in the mix and we want to find the variable so that it's a probability distribution. So we need what to happen? 1/6 plus 3/6 plus 1/6 plus y should be 1. So this is 4/6, which means y needs to be.
1/6.
That's 5
It's
plus
5
6.
5 out of 6.
Alright, so y needs to be 1 minus 4/6.
5 out of 6.
5 out of 6.
5 out of 6, which is 1/6. Same idea here. We need y plus 1 plus y plus 3 plus y plus 2 to be equal to 1. So the y value here was 1, 2, 3, 4 y's. There's 1 minus a bunch of stuff over 4.
1 minus 6. It's going to be y is equal to -1.25.
negative 5/4 or minus 1.25. Does it make sense for that value?
No, because then that y would be negative.
Makes no sense because the probability of 7 would now be negative. It's bigger than 1 in absolute value and it's negative, so it's wrong on 2 counts. What about this one? So here we need y plus 1 plus y plus 1 plus 0.1 plus y plus 0.9 to add up to 1. This means y is equal to minus 2/3. Make sense?
No. Oh, well. Yeah, I guess that makes sense because when you add them, they're all positive.
Yes, it makes sense because they'll all be positive once you actually plug that number in. So this is 2, 5, 7, 9. So this is minus 2/3. This guy would be 1/3. That would be 1/3. This would be 2/3, like 0.6. So it's 0.1 is going to be like 0.4 something. And this would be minus 0.6 plus 0.9. So this would be roughly 0.3. So all the values here end up being positive. Maybe not points, it's like 0.7.
Isn't 7 just
Is
0.1?
it changed?
7 stays the same.
7, yes, it's 0.1. I was actually subtracting. There's no y in here. Okay. So we sort of see how probability distributions work. They have to, some of the probabilities have to be 1, and you can't have any negative numbers down here because there's no such thing as a negative probability. You also cannot have a number that's greater than 1 in absolute value down here. So if there's a 2 down here, something's wrong, right? It's not a probability distribution, or you made a computational error. Now we're going to talk about computing the mean of a probability distribution, which we know is a discrete random variable. Mean, or as it's called sometimes, the expected value. Right, the value that will be obtained on average of a discrete variable. Distribution. So this is the formula. The expected value is the sum of x times the probability of the x value for each x value. So this is, if you want to be pedantic, I goes from 1 up to n. This is xi, p of xi, something like that. Sum of x times p of x. And so that's called the expected value, right? You figure out how many different values can occur, what are the chances that they can occur. So this occurs with this chances, this occurs with this chances. If you multiply all these and add them all up, you will get the average value that you expect to occur. So we can have an example. Again, we sort of mentioned this before. We'll probably end there, end after that example today. Some cool things to tell you next time, though. We'll do factorials and combinations. The binomial formula. And Poisson distributions. No, right? And then we're going to show you what kind of problems you can solve knowing those. Things get a lot easier and you can count a lot more efficiently. when I tell you about those guys. Well, we'll end on expected values today. We're not done with chapter 13, but even if we finished, I wouldn't let the homework be due before the test. So up to homework 11 is due on Monday. But the homework's for 13 and later, if we finish them, we just hand them in after the test. We're almost done. We're only going up to chapter 14 actually, so we are very nearing the end. You can see the light at the end of the tunnel. You're walking down the street and the guy says, hey, psst. Hey, psst. Yeah, you want to play a game, man? It's $1 to play, right? And he's like, all right, you just roll this dice, man. It's a totally legit dice, I promise you. Okay, you trust this guy. All right, you seem trustworthy. All right, I'll trust he's a fair dice. All right, so here's the game, man. Roll the dice once, lands on a 6, I give you $3, right? Lands on a 3, you get nothing. 1, 2, or 5, you have to give me another $1. Lands on a 4, you win $1. And is this a good game? Do you want to play this game? How much do you expect to win if you do play? Right? In the long run, on average, how much do you want to win? So, and is it worth playing? That's the question, right? Do you actually play this game? You'd be like, sucker, and walk away. Okay. So now what we can do is we can use a discrete random variable to measure our gain. So let's do that. Let x equals gain per play. Then x is, what are the possible values that x can take on?
1, 2, 6.
No, it's
Nope.
It's
X is measuring how much money I
6
earn.
or 1. Oh, 6 or 4.
Well, the
No.
biggest possibility is that you land on 60.
No, it's only
So it's,
6 or
no,
4.
it's gain.
Right, so remember I pay $1 to even start
So
playing,
it's
right? One
negative-
possibility is that I win $3, right? So in
Yes,
that
so
case,
it's
my
2.
gain would be 2.
Then -2,
The
-1.
other possibility is I get nothing, which means I lose $1. So there's a chance I lose $1. There is a possibility of me losing another $1, right? So I pay $1 to start playing, but if I roll any one of these, I lose another $1. So that's -$2. There's also the situations, if it lands on a 4, I win $1, which means I don't really lose anything. So I pay him $1 and he gives me my $1 back. Okay, we'll do. All right, so these are the possible values for x. But there's a chance you can gain $2.
Okay, so there's a chance you can lose.
Huh? Yeah, but you can gain $2 though. All right, is it worth it? How do we figure out if it's worth it? Well, it would be good if we know how much we expect to get, right? What's the expected value? So to find that, what do we need to find? A probability distribution, right? So we can just see the numbers and do the math, right? So here's my x and my p of x. Possible values are -2, -1, 0, or 2. Now, what is the probability that it lands on a 6?
1 out of 6.
1 out of 6, right? In that situation, I gain 2, so here it's 1 out of 6. Right? We're assuming it's a fair dice. This guy is obviously trustworthy. Doesn't matter, he has a black coat calling to us from the shadows. He seems honest. Okay, so then if it lands on a 3, you get nothing, which means you actually lose $1 in effect, right? What is the probability that it lands on a 3?
1 out of 6.
So that's here, 1 out of 6. And if it lands on a 1, 2, or 5, you lose $1, which means ultimately you lose $2. What is the probability that it will land on a 1, a 2, or a 5?
3 out of 6.
3 out of 6. And we could also look at this, but we can also make sure that these add to 1. So it's just another 1 out of 6. So this is the probability distribution for this game. So this means I can figure out how much do I expect to win on average. Well, it's just going to be the expected value. We're going to take that -2 times 3 out of 6 plus the -1 times 1 out of 6 plus 0 times 1 out of 6 plus 2 times 1 out of 6. So this would give us what? This goes with that 3 times, so this is basically -1 minus 1/6 plus 1/3. Which I can just think of this. Think of this as 2, 6, and then this as 6 out of 6. So what do we have?
-5.
-5/6. So is it worth playing?
No.
Nope. In the long run, you will lose 5/6 of $1. So if you play the game 60 times, you'd lose $50 basically. That's what you can expect. So not worth playing. As fun as it might seem to be playing this game with a guy in a dark alley who's very suspicious. In that case, I'll pass. Okay, we'll end there. Again.